Hello, I am Seema and welcome to part 30 of the chapter Organic Chemistry, Some Basic Principles and Techniques. We have been doing some electron displacement effects on covalent bonds, and the different effects that we have done in the previous videos are inductive effect, resonance effect and electromeric effect. In this video we are going to do the fourth and the last effect, that is hyperconjugation. Now, as in the previous videos I explained that the effects may be temporary or permanent. Permanent effects are effects which are present due to some substituent or something inside the molecule, an atom or a substituent present inside the molecule which causes this effect. And therefore, since it is present in the molecule, it's a permanent effect. And a temporary effect is one which is due to something that is outside the molecule, like the attacking reagent. Therefore, such an effect would be a temporary effect. Hyperconjugation is also a permanent effect. When we say it's a permanent effect, it means that there is something within the molecule which is causing this effect, and that is why it is permanent. So, having dealt with the part where it is a permanent or a temporary effect, we understand that it has all to do with the substrate molecule and nothing to do with the attacking reagent. The molecule itself has something in it which is responsible for this effect. Whenever there is a delocalization of electrons causes polarity, it creates polarity 1. Secondly, it may cause a dispersion of charges, it may cause the movement of the charge, like we saw in resonance that the negative charge or the positive charge revolves in the entire chain. So this delocalization of electrons, it causes stability. Hyperconjugation is somewhat similar to resonance in that way that there is a jumping of electrons that is possible due to hyperconjugation. Therefore, just as in resonance we notice that it leads to the stability which is known as the resonance stabilization energy, if you remember. And if you do not understand what I am telling you, I would encourage you to watch that video where I explained the resonance effect to you. So, whenever there is a delocalization of electrons and there is a charge distribution, that is distribution of charges which is not static at one atom, you get more stability, it leads to more stability. Therefore, if hyperconjugation is an effect which causes that, it is a stabilizing effect. So we say it is a general stabilizing interaction. So it generally causes stabilization. Why? Because it is causing the movement of electrons, and due to the movement of electrons, the charges are not static. And since they are not static, it causes a stabilization. What happens in this effect? What are the kind of atoms which would, or what is the kind of a molecule which would show such an interaction? When you have the sigma bonds of a methyl group, let us say this is a methyl group, all the CH bonds in the methyl group are all sigma bonds because they are made up of sp3 hybridized carbon orbital and the 1s orbital of the hydrogen. Whenever you have the sigma bond, sigma electrons of the methyl group, and if the adjacent carbon has got an empty orbital due to some reason, or if the next atom is, let us say, unsaturated and therefore it has pi electrons, so the sigma electrons get conjugated with the empty orbital or with the double bond, the multiple bond. And when such a conjugation arises, then what have we noticed in resonance? In resonance we knew that the system was conjugated. There was a double bond, a single bond, a double bond, a single bond, a double bond, a single bond. So what happened? Electrons of the double bonds, that is the pi electrons, they got conjugated with the pi electrons of the next carbon. If this carbon has got a pi bond here in this direction, the next carbon atom is attached by a single bond, but this neighboring carbon atom has got a double bond with the next carbon atom. So as a result, what happens? A double bond, single bond, double bond, but these two atoms have got both double bond and single bond. On one side it's a double bond and on one side it's a single bond, which is causing the pi electrons, which is allowing the pi electrons to jump. If one of the pi electrons comes here and forms a double bond, the next pi electrons will jump further and result in the formation of that, turning that single bond into a double bond, and that is how the charge travels. In this case also, due to this conjugation that is created not by pi electrons, it is sigma electrons on one side which are getting conjugated with either an empty orbital or by the pi electrons. Such a conjugation that creates a kind of a false resonance, a masked resonance. It can also start acting as resonance. And when this happens, this type of resonance, which is a false, it is not a true, it's not actual resonance as we had studied, where there were only pi electrons which were involved. In this case, it is sigma electrons which are in conjugation with a pi bond or with an empty orbital. And since they have that empty orbital or the possibility of the pi electrons moving and those electrons taking their place, so that possibility of their moving from their place is known as hyperconjugation. So in hyperconjugation, it is not the pi electrons which are moving, it is the sigma electrons which are getting conjugated, and therefore they are available for movement. I'll explain this better. Once I read this, I come to this diagram again, I'll explain it to you. So what does hyperconjugation involve? It involves the delocalization, the sigma electrons, the delocalization of sigma electrons of the CH bond. If you look at the CH bond, it's a sigma bond because this is a methyl group. It is an sp3 hybridized carbon, and one of those sp3 hybridized orbitals is forming a bond with this hydrogen. One is forming a bond with carbon, and these three are forming bonds with hydrogens. And one of these hydrogens, it kind of gets parallel to an empty orbital here, right? So we say it involves the delocalization, which means movement of sigma electrons of the CH bond of the alkyl group directly attached to an atom of unsaturated system or an atom with an unshared pair p orbital, unshared p orbital, or an empty p orbital. So if it has this empty p orbital like you have it in this carbocation, so what happens, these sigma electrons, they can use this empty orbital and they can jump into this empty orbital. So if they move from their position, they have been delocalized, and that effect is known as hyperconjugation. Let me read this again. It involves the delocalization of sigma electrons of the CH bond of alkyl group directly attached to an atom of an unsaturated system. This could be pi electrons, and therefore it would be an available orbital, or to an atom with an unshared p orbital, for example a cation. The sigma electrons enter into partial conjugation with the double bond or the empty orbital. For example, you have this ethyl carbocation. In this, what do we see? Orbital diagram showing the hyperconjugation in ethyl cation. In this ethyl carbocation, the sp3 hybridized hydrogen can be in conjugation with this empty orbital, and therefore these electrons, the sigma electrons, can move into the empty orbital. Now, what is interesting here is that there are 3 CH bonds, and the possibility, and according to molecular orbital theory, these electrons, this is only a probability picture. So there is a probability of this sp3H also being in conjugation with this, or this hydrogen, the electrons of this sigma bond can also be in conjugation. So any of these 3 can be in conjugation with this empty orbital, and they can cause the hyperconjugation. So what do we understand? The more the number of sigma electrons, the larger is the chance of hyperconjugation. So if instead of these 2 hydrogens we had methyl groups, we had methyl groups here also. For example, if I had a CH3, then those hydrogens could also have conjugated. Those sigma electrons could also have conjugated with the empty orbital. So the larger the number of methyl groups, greater will be the chance of hyperconjugation. Why? Because hyperconjugation is due to the movement of sigma electrons which are bound to the carbon adjacent to the carbon which either has a double bond or the carbon which has an empty orbital. Now these electrons of the sigma bonds, they can be in partial conjugation. We will not say proper conjugation, because in proper conjugation there should be a double bond, single bond, double bond. This is not a double bond, it is a sigma bond. And a proper sigma electron of sigma bond which is kind of acting as if it doesn't know it is a sigma electron, a pair of sigma electrons, and they also can conjugate partially and therefore move. Due to any movement of electrons, stabilization is caused. You remember when I told you that it's a general stabilizing interaction. So this interaction, that is hyperconjugation of the sigma electrons, causes the stabilization of the carbocation, because the electron density from the sigma bond helps to disperse the positive charge. Now, as I told you, the more the number of CH bonds attached to this carbon which has got an empty orbital, if this hydrogen was also a methyl group, this hydrogen was also a methyl group, what would have happened? You would have had more possibility of hyperconjugation. So we take this example and let us see what are the different hyperconjugation, what should we say, canonical forms which are possible. In the carbocation, that is ethyl carbocation, you have CH3, CH2, and the positive charge is on the carbon. Now hyperconjugation occurs, and this hydrogen, this sigma bond, it comes and occupies the empty orbital of this carbon. So in this molecule, when hyperconjugation occurs, this hydrogen, the sigma electrons of this hydrogen, of this carbon hydrogen, that forms a bond here, that is, it moves to this carbon, and therefore a double bond is formed here. But this carbon, since it was positively charged here, it loses the positive charge by getting the electrons from this hydrogen. And the hydrogen becomes positively charged, yes, but there is no bond anymore between the carbon and hydrogen. There is no bond between them because there was only a single sigma bond which is lost due to this partial conjugation. This is where hyperconjugation is different from resonance. You know, time and again I'm talking of resonance here because this is where you might get confused between resonance and hyperconjugation. The reason why we studied inductive effect and electromagnetic effect and studied the differences was also this, to make it clear what's the difference between the two. Here there is a chance that you might confuse it with resonance. But then the first thing, in the case of resonance, you have only pi electrons which are delocalizing. But in hyperconjugation, it is not pi electrons, it is the sigma electrons which are getting delocalized. Both are permanent effects, of course. So here, take a look. How is the charge dispersing? So this hydrogen, when it hyperconjugated, it gave the carbon lost its positive charge, and the positive charge came on the hydrogen, but which now no longer has a bond. Let us assume that instead of this hydrogen, it was this hydrogen which hyperconjugated. Then the positive charge would come on this hydrogen, this bond would be lost, and the double bond would be formed. The positive charge of carbon would be lost, obviously, because it got the 2 electrons from hydrogen. And therefore, this carbon becomes neutral. And there is no bond between the carbon and hydrogen. And in this structure, you see, let us see that take this hydrogen, which is hyperconjugating, then this will become positive. The rest of the structure remains the same. These two are proper bonds. This is a double bond. Carbon loses the positive charge because it got electrons from this hydrogen. But this hydrogen becomes positively charged with no bond with carbon. So just as we made canonical structures in the case of resonance structures, in the same way we get these structures in the case of hyperconjugation also. But the difference here is that there is, in resonance, there was still a bond because it was the pi electrons which were moving and the sigma bonds were where they were. Here, the bond is lost. When hyperconjugation occurs, the sigma bond itself moves. Therefore, no bond exists between the atom that causes the hyperconjugation. Now, and since the positive charge is moving from place to place, from one position to the other, there is a dispersion of the positive charge, and therefore we said there is a dispersion of the positive charge which causes stability. greater the number of alkyl groups, greater will be the hyperconjugation. If these two were not hydrogens, they were also methyl groups, then those hydrogens would also have participated in this hyperconjugation, and you would have got more structures with every hydrogen which can hyperconjugate. So the greater the number of alkyl groups, greater will be the hyperconjugation, and greater the hyperconjugation, greater will be the stabilization of the cation. Why? Because greater would be the delocalization or dispersion of the charge. The charge will be even more dispersed between, here in one methyl group you have 3 hydrogens in which the charge is being dispersed in addition to the carbon. But if you had another methyl group, there would be 3 more hydrogens, so 6 hydrogens. If there was another methyl group here, then it would have been 9 hydrogens. So greater the number of methyl groups, greater are the number of hydrogens available for hyperconjugation, and greater is the dispersal of charges, and greater therefore is the stability due to hyperconjugation. Therefore, from this, what do we understand? That if there is a carbocation which is tertiary, like C, the positive charge is here, and here you have methyl groups, all 3 are methyl groups, like here, a methyl group here, a methyl group here, and a methyl group here. So a tertiary carbocation would have maximum hyperconjugation, and then would be a secondary one, then would be the primary, and the methyl carbocation would have least hyperconjugation. So that is the sequence of hyperconjugation, the stability caused due to hyperconjugation in different cations. Hyperconjugation is also possible in alkenes and alkyl arenes. It is understandable. In alkenes and alkyl arenes, you will not have the positive charge. That is, it's as in carbocation, the empty orbital. Instead of the empty orbital, you will have the pi orbital, the p orbitals which are causing the pi bond formation. So again, if this is a methyl group, if this is the methyl group which is attached in propene, then in the case of this carbon which is forming a double bond with this carbon, there's a double bond here, a sigma bond and a pi bond. Now this pi bond and the sigma electrons of this bond, they are partially hyperconjugated, due to which these electrons can move here, and since they move here, what will happen? Since they move here, the delocalization has occurred, and therefore this would also show hyperconjugation. Now hyperconjugation is also known as no bond resonance. It is understandable that resonance is created, but you clearly see that there is no bond with the hydrogen that is causing the hyperconjugation. So we say this is a resonance, a kind of a resonance, but in which there is no bond with the atom which is causing resonance. So a second name has been given to hyperconjugation, which is no bond resonance. The CH bond possessing the partial ionic character, it possesses the partial ionic character due to resonance. Take a look here now. CH3, C double bond CH2. So CH3, what is this? This is propene. In the case of propene, let us say that hyperconjugation occurs with this hydrogen. If this hydrogen is hyperconjugating, then the 2 electrons will form a bond here. If the 2 electrons form a bond here, the hydrogen becomes positively charged, but carbon cannot form 5 bonds. So as soon as this forms a double bond, the double bond here, it moves to this carbon, giving it a lone pair of electrons, and the negative charge comes on this carbon. Do you see? That is what happened in this case. So a negative charge will be formed on this carbon, and as soon as a negative charge is formed on this carbon, you have both a polarity created in the molecule, positive charge on the hydrogen and negative charge on the carbon. If you really look, the hydrogen which is positively charged is not actually bound to the molecule. Then in another structure, if it was the other hydrogen undergoing the positive charge or hyperconjugation, then let us say this one, this is another canonical form. This hydrogen is hyperconjugating, again this carbon would have the negative charge, but the second bond will be formed here, and the third structure would be where this carbon is hyperconjugating. So we get the resonance structures, a kind of resonance structures. It is not true resonance if you really see, or you would say it is a resonance where bond between the hyperconjugated atom and the molecule is missing. So we call it a special case of resonance, that is a no bond resonance. Right? So these are the different structures that you would get as a result of hyperconjugation in the case of propene. So that was hyperconjugation, and these were the different effects. And with this, I'll wrap up the video. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.